high resolution of what cosmic reionization, that kind of the schematic picture of what cosmic reionization is. So early stars formed in the universe. These stars possibly produced quite a bit of ionizing photons. And these ionizing photons propagated outwards from the stars into the IGM. And if there are sufficient number of stars producing sufficient number of ionizing photons, these early stars could actually completely reionize the IGM. Fairly simple picture, but it's heavily complicated by the fact that stars reside in galaxies, and galaxies have these pesky things called neutral gas. And these neutral gas is actually the seeds for the first generations of stars. But this neutral gas also contains a large amount of H1, which absorbs these ionizing photons, such that only a fraction of the ionizing photons that are produced by the first generation of stars can actually escape these galaxies and make it into the intergalactic medium. And one of the most uncertain parameters about whether high-mass stars in the early universe can actually reionize the universe is what this fraction of total ionizing photons that are produced actually escapes these galaxies. This is called the escape fraction. And observations kind of suggest that if high-mass stars are the ones that reionize the universe at redshifts between 6 and 10, you need about 10 to 20% of the total ionizing photons produced to actually escape these galaxies. And that's pretty hard, actually, with fairly moderate H1 column densities to actually reionize the universe. So there have been some kind of schematic suggestions of ways in which you can get around this problem of having neutral gas within your ISM. And of course, everyone always falls into these two camps, these broad brush approaches. But by and large, what is thought is that there's either something called a density-bounded regime, where you actually have a fairly low H1 column density within your galaxy, below about 10 to the 17.2. And that just means that there's not enough H1 gas within your ISM to absorb all of the ionizing photons that are produced. And so since there's not enough gas, the photons are able to free stream out of the galaxy and into the IGM. The second kind of schematic picture is what has sometimes been referred to as the picket fence model, where you have these low density channels through an otherwise optically thick H1 medium, and these ionizing photons are able to actually propagate out through these low density channels and into the ISM. And it's kind of been hotly debated which two of these are in reality what emits ionizing photons into the intergalactic medium. So in order to test that, you can start looking at galaxies that emit ionizing photons. And up until about 2 or 3 years ago, the situation was pretty bleak and pretty dire. We only had a sample of 2 or 3 galaxies at any redshift that emitted ionizing photons. But through some heroic observational efforts, and this is a fairly long list, but it's not exhaustive, of many people in this room, we have compiled a sample of 20 to 50 galaxies at any redshift that emit ionizing photons. And if you look at the properties of these galaxies, so the red galaxies in all of these plots are galaxies that actually emit ionizing photons. These galaxies are largely low mass, highly star-forming, and metal poor. And also, a key defining characteristic seems to be that they are extremely compact. So here are 2 UV images of 2 galaxies in the local universe that emit ionizing photons with escape fractions of 7 to 72%. And so what we did, along with Simon Gasnet, is we took a sample of 15 galaxies from the HST COS archive with far ultraviolet UV spectroscopy. And this far ultraviolet UV spectroscopy is great because it contains something called the Lyman series, which are UV absorption lines of H1 gas. And within this sample of 15, there are 9 confirmed Lyman continuum emitting galaxies. So we can look at what the H1 UV absorption profiles look like between Lyman continuum emitters and non-Lyman continuum emitters to kind of get a handle on what the H1 properties are of galaxies that emit Lyman continuum photons. And so here on the left, I am showing two Lyman series absorption lines, Lyman delta in blue and Lyman delta in red and Lyman gamma in blue. And the first thing you notice is the shape. So the width and the depth of these two lines are very similar, even though they have very different oscillator strengths. And so what this implies is that the H1, the Lyman series, is actually saturated. And so in some ways that's unfortunate because you can't get precise column density estimates on it. But you know that the Lyman series saturates above H1 column densities of about 10 to the 17. And that's important because in order to emit ionizing photons through some sort of density-bounded regime, you need column densities below 10 to the 17.2. So just from the fact that these two lines have very similar profiles, widths, and depths, shows that the density-bounded regime is not how ionizing photons escape these galaxies that we are looking at. Further, you can see that the depths of these lines do not reach zero flux. There is some sort of residual continuum that is escaping through this H1. So what that implies is that there is some sort of low density channel through which the continuum is actually able to escape through. And so that's called the 1 minus the covering fraction is this kind of residual flux, where the covering fraction is a measure of the porosity of the H1 gas. And so that's a Lyman continuum emitter. You can kind of compare that to an H1 profile of a non-Lyman continuum emitter. And you see that non-Lyman continuum emitters have completely black H1 profiles. There is no residual flux escaping from these galaxies. So the difference between these two profiles is showing you why some galaxies emit ionizing photons here on the left, and some galaxies do not emit ionizing photons on the right. And so Simon did quite a lot of work, and I've kind of glossed over a lot of the details, but I encourage you to go and talk to him about his work. But just to summarize it, he found that galaxies that are known to emit Lyman continuum photons generally have H1 covering fractions less than 1, substantially less than 1. Whereas galaxies that are known to not, or not with well-defined Lyman continuum escape fractions, generally have very high H1 covering fractions. So it's this difference between the two that's kind of the smoking gun for Lyman continuum emission. And so there's these low densities channels that we think that are emitting, that allow for these ionizing photons to escape through these things. So what creates these low density channels? And one suggestion has been extreme feedback. But when we look at the silicon-2 absorption line properties, so this is kind of a tracer of the outflow properties of these Lyman continuum emitting galaxies, we find that the red points, again, are the Lyman continuum leakers. They have outflow velocities that are very similar to local galaxies that do not emit Lyman continuum photons. So you don't actually have extreme outflows from these galaxies to create these channels. And similarly, the equivalent width, a proxy for kind of the amount of gas within your galaxies, kind of follows along this trend with metallicity for local galaxies. So it doesn't seem like extreme outflows are what does it. A possibility could be the geometry of these. Like I said before, all of these galaxies are very compact geometries. And very compact, low mass geometries could facilitate the creation of channels more easily with a given supernova injecta. And so what does this geometry, this channel geometry, tell us about indirect indicators of Lyman continuum escape? Well, we can use the H1 covering fraction along with the measured dust properties to actually predict the escape fraction of ionizing photons using kind of the canonical radiative transfer equation. And we find that 1 minus the covering fraction, along with some dust inclusion, actually very accurately reproduces the observed Lyman continuum escape fractions. So that's implying that if you just account for these low density channels and dust, you're able to reproduce and predict the escape fractions. And using that radiative transfer equation, you can break up the relative contributions of covering fractions. So this is if you just had dust-free channels through which ionizing photons escaped. You see that you would predict much higher Lyman continuum escape fractions than are actually observed, which are these purple points down here. Further, dust substantially reduces the number of ionizing photons that you emit through these galaxies, but even dust is too large. So what you need are these dusty, low density channels in order to really reproduce the observed escape fractions. And H1 is great, but it's not observable at high redshifts for, epoch of reionization sort of studies. And so what we would like is a tracer that is redward of Lyman alpha. And so we found that there is a correlation between the silicon-2 covering fraction and the H1 covering fraction. It's not exactly 1-to-1, which is this line. It's kind of offset. But this empirical relationship allows you to actually correct the silicon-2 covering fraction for a neutral gas covering fraction. And when you do that, you can, again, reproduce the observed Lyman continuum escape fractions. And since a lot of you are into Lyman alpha, we also looked at how you can use this channel approach to predict Lyman continuum escape from Lyman alpha escape fractions. So what we did is we took the Lyman alpha escape fraction and just corrected it for the more dust that the Lyman continuum photons experience. And we found that by doing this in this sort of low density channel approach, you actually can recover or predict the Lyman continuum photon escape fraction. So this kind of suggests that Lyman alpha and Lyman continuum photons are actually escaping through similar sorts of low density channels within the H1 distributions. And this ties in nicely to Elena Henry's work with magnesium-2 escape fractions too. It could be a very similar sort of escape mechanism. And finally, just going along that theme a little bit, we found that the Lyman alpha peak separation, which is oftentimes a very good proxy for Lyman continuum escape, this is usually thought of as a density probe. We found that the Lyman alpha peak separation scales with the silicon-2 equivalent width. And equivalent width is a little hard to interpret physically because it could be the depth or it could be the width of your line. So it could be the amount of gas in your along your line of sight, or it could be the covering fraction. And so kind of combined with what we've been seeing before, it seems like this Lyman alpha peak separation with silicon-2 equivalent width is suggesting that the silicon-2 covering fraction is largely driving this trend. So just to summarize here, we used the Lyman series UV absorption lines from 9 Lyman continuum emitting galaxies, as well as some non-Lyman continuum emitting galaxies, to show that ionizing photons likely escape through low density channels. And this low density channel approach, along with the dust attenuation, can actually accurately reproduce the observed Lyman continuum escape fractions. There are some ancillary indirect methods of reproducing the Lyman continuum escape fractions, which are kind of nice and handy for epoch of reionization work, which all kind of suggest that Lyman alpha and Lyman continuum may be physically related due to the low density channels through which they escape. Thank you.
Thank you. Questions?
Yeah, in this, do you have Lyman alpha profiles for these like samples? And then, I mean, is it consistent for such a low scale? Like, do they have actually emitting Lyman alpha at line center like for such a covering factor of H1?
So yeah, so by and large, the Lyman alpha escape fractions of the Lyman continuum emitters are double peaked, red dominated double peaked, but with a pretty substantial blue bump. They are not blue, they're not zero velocity center.
But zero flux at line center.
Say that again?
Zero flux at line center.
They do not have zero flux at line center, no. They have flux at line center.
And in this plot you showed, sorry, can I ask a follow-up? Thanks. In this plot where you showed with F escape, Lyman continuum versus covering factor, where would the non-leakers fall on this plot?
They would all fall, so let's go back to this one. So all of the non-leakers basically have unity covering fractions. So 1 minus 1, they would fall all down here.
More questions? Okay. Well, thank you very much. Okay. Next speaker is Rohan Ido. He's going to talk about constraints on the escape of Lyman continuum from star-forming galaxies at redshift 2 to 4 from Hubble Deep UV legacy surveying.
Excellent. Good morning, all of you. My name is Rohan Ido, and the work that I'm going to present, I did with all these wonderful people who you probably know as amazing scientists, but they also happen to be really amazing mentors, and I'd like to highlight that to begin with. This is the outline of my talk. I'll begin by giving you a new reason to care about the Lyman continuum escape fraction that we've already heard so many reasons to care about over the last couple of days. Then I'll talk to you about this wonderful survey that we have with the Hubble Space Telescope. And finally, I'll wrap up by linking, hopefully, tentatively, the Lyman continuum escape to stuff that we can actually observe with JWST at high redshifts where it matters. So on the left here, I show a recent result. So this is the drop in star formation density reported recently between redshifts 8 and 10. I'm sorry, this is cutting my screen in a way that is not conducive. I'm sorry.
Change the resolution. So if you go to your app, and then system preferences, back, displays, can you do mirror displays? That might be better. Try that now. So just try to go back into the full screen of your PowerPoint,
All right, with this.
your Google Slides. Just click on it and then try to go full screen. There you go.
So, other than finding great channels for Lyman continuum escape, John also finds great channels for the escape of slides into the universe. Okay, going back to where we started. So I'm going to give you an extra reason for why you should care about the escape fraction, which is this recently reported dearth of galaxies at redshift 8 to 10 has direct implications for how many ionizing photons are available in the early universe. So what I'm doing here is with this wonderful empirical model from Takila 18, from Sandro Takila, we essentially reproduce this drop in number density, and then we generate ionizing photons using the MIST models. And we see that compared to previous studies that have kind of looked at this ionizing budget, we do not have those many photons in the early universe. So what this does is it immediately pushes the timeline of reionization to be a very stringent one. So you see here a lot of action is happening essentially between redshift 6 and 8-ish. The universe goes from more than 90% neutral to less than 10% neutral. And the complementary demand that this dearth of photons in the early universe places is on the escape fractions. So what I'm showing here is I've left the escape fraction as a free parameter in this empirical model. And we try to constrain it against all this data from the neutral fraction at various redshifts, from the recently discovered quasars at greater than redshift 7.5. We have the condition that reionization should end by redshift 6, and then you have the latest Planck tau. And each of these different data sets places its own constraint on the escape fraction, but the upshot here is that you need, assuming a constant redshift invariant escape fraction, you need about 20-ish% for star-forming galaxies down to MUV minus 13 to pull this off. And this, of course, doesn't really sit well with current observations, at least of the bright galaxies that we have out to redshift 3, 4 even. There's several caveats that apply, which is to say that maybe our samples are not super faint enough, which I talked about yesterday. Maybe the escape fraction is varying really wildly with redshift and with other properties. But this general fiducial model that a lot of people use as a benchmark for what should the minimum be for star-forming galaxies to breach, given these new data, is pretty significant, which of course motivates going out and trying to measure this well and better for like subsamples that have not been touched yet. Which is where I'll introduce this survey that we have with the Hubble Space Telescope. It covers these fields. It overlaps very strategically, of course, with the Candles Deep footprint in Goods South and Goods North. And it is basically imaging in these two filters. So you have F275W and F336W. And over here, I show the IGM transmission curve. One of them is from Akio Inoue. One of them is from the typical Madao one. And you see that at these particular redshifts, at redshift 2.4, at redshift 3.1, these filters are perfect in terms of collecting photons that are just blueward of the Lyman break. So essentially, this large imaging survey can be used to find Lyman continuum leakers across a fairly large area to a pretty deep depth. And that's essentially what I'm going to talk about here, how that whole effort went. But before that, I'd like to advertise for a second and say that these UV images are all wonderfully reduced, free of artifacts, made into amazing catalogs for easy usage, and available en masse. And in fact, they were so pretty that they were featured as the Hubble Picture of the Week on the 20th. Not just once, but twice. They just couldn't get enough of our UV images, so there's no reason you should not be headed to MAST right after this talk and add them to whatever science program you have. So let's look at some constraints now on the Lyman continuum problem that we got from this really unique data set in the regime of stacking. So a lot of people have done this, but the key advantages that you gain from Hubble is you have exquisite spatial resolution. So a lot of the concerns about interlopers and stuff like that can be addressed really well and really head-on. And we have all these newly assembled spectroscopic samples thanks to recent surveys like the MUSE-wide, the MUSE-deep. In the north, you have MOSDEF, and you have this perfect storm of redshifts right in this range where we need them the most for this sort of stacking. So over here, we show a tentative detection in the F275 band where you expect to see Lyman continuum. It's not super significant. It's at the 2-ish sigma level. And over here at redshift 3, we stack all these sources, which are Lyman alpha emitters, O3 emitters, basically every redshift we could verify, and that was robust in the literature in this tiny range. And we essentially find an upper limit. This is the band you should be looking at, and there isn't really anything there. And over here, this is the band you should be looking at, and there's kind of sort of something there. To guide your eye, we have shown model spectra. The features are here with the IgM, without the IgM. Sorry, without the IgM, with the IgM, and this is the point that we are saying is perhaps a detection. And then, of course, you dice this based on UV magnitudes and say, let's look at the fainter sources versus the brighter ones. And I'll emphasize that this is preliminary, but it turns out that the F275 detection does seem to be real, and it seems to be tracking this very bright population, which seems to be very Lyman alpha bright and Lyman alpha emitting. And this corresponds to this particular detection here, and we have a number of around 10-ish%, 10 plus or minus 4 at redshift 2.5, which is a measurement that just hasn't been possible before at these redshifts that we are able to make thanks to this wonderful data set. At redshift 3, we are only able to muster upper limits as shown here, and we are essentially able to say that it's maybe less than 11-ish% at 2 sigma. Again, preliminary, but very intriguing and promising. And then, of course, we look at individual sources in this huge footprint that we have and that overlaps with all these recent amazing redshift surveys. I'd just like to put in a slide here to remind you that finding individual detections that are really convincing at these high redshifts is extremely tough. So here is, I've just listed all the things that could possibly go wrong with a source that seems that it's a Lyman continuum emitter. You have interlopers from low redshift, you have like spectroscopic redshifts taken from the ground that are wrong or that are merged. So much happens. And then here I've highlighted things that we've done to ensure that our sample is not compromised by them. Over here, I'd like to highlight a recent study by Jones et al., where all the sources in their sample were very well detected in these UV bands, but every single one of them, except for one AGN, and I believe there were 6 or 7, turned out to be this sort of like chance superposition, where there was like a low redshift interloper that only showed itself in a very deep spectrum. Here I show VJH images, which are sort of like a poor man's way of finding interlopers when you don't have spectra. And this is a classic case of some sort of superposition where you have multiple components that show up in different color. So given that we realize how difficult and how like amazingly complex this is compared to just finding a detection in this blue-white band, let's go ahead and actually look at some of these sources that we believe are robust. Oh yeah, and I also wanted to highlight like an AGN sort of candidate where like this indeed is a beautiful detection, but look at how like unresolved this point is here. So if you're looking for the star-forming galaxies contribution to the Lyman continuum budget, then these are not the sources that you want. So these are detections that we believe are robust. These are all in the good south field, mostly from MUSE and 3D HST. This is the band that is probing the Lyman continuum. And these are the detections that we see at levels that we believe, which is more than 3 sigma, and that satisfy all our checks. They're not AGN, they're not interlopers, they're not any of those problematic things that we just described. The other thing that I'd like to draw your eye to in this particular set of images is the F275 band and how critical it is to this whole endeavor. So even though it's not probing the Lyman continuum is here, but it being just blueward helps us remove all sorts of interlopers that do show up in the immediately blueward band, which is something a lot of studies suffered from earlier, which they would have been able to bypass with this blueward band, which would have showed the contamination like here, you see. And that is one of the conditions that we set while looking for these sources. We have a bunch of sources in goods north as well. And again, the same thing. We look at clean F275 images. We look for robust F336 detections, which are which contain the Lyman continuum at these redshifts. And let's go into some of the properties that I want to highlight about this emergent, recently discovered sample. Let's zoom in on one of them, yeah? So this is a really compact source that we are seeing here, which of course just looks like a splotch, and like there's probably like just like a noise, some noise in the background at first look. But zooming in, you see that this is where the source that we are claiming is, and this is a non-ionizing UV. And at the exact same position, we draw a contour to guide the eye, and this is the claimed Lyman continuum. And then, of course, because you have HST, you're able to do this sort of thing where even though there's a very close-by neighbor, only a few pixels away, you can fit a photometric redshift to each of them and see where they lie. From the ground in U-band imaging, this would have been one big blob, and you would have probably discarded it for being at lower redshift. And just looking at the statistics, what is the rate of detection, right? Like how many sources, how many hundreds of sources did you have to look at to get this sample? So we looked at all these, so these are the numbers that you should look at in terms of like what our large input spectroscopic sample was, the whole compilation across the literature. But then I would like to highlight these numbers as the ones that actually matter in terms of which are the sources for which we can definitely rule out LYC leakage, Lyman continuum leakage. So these tend to be the brighter sources, right? Because even if you are not seeing Lyman continuum from a fairly faint source, that doesn't mean that that source is not leaking Lyman continuum. So what is actually the number in your sample for which you can rule out to a very fair degree that there isn't Lyman continuum leakage? So that is the number that I highlight here. So just looking at percentages, like how many sources can you rule it out for, how many sources are actually detected, we have about a detection rate that is fairly on par with the Tidal 18 results that were shown yesterday. And we are about a factor of 3 lower than what is claimed in the recent LACES papers. Over here, I've plotted this tidal sample for comparison. As Ryan highlighted yesterday, it is chosen to be fairly bright and easily observable, so it neatly sits over here. The error bars are very tight and snug. We, on the other hand, like go all the way down, but our error bars tend to be huge in the faint end. And we see this like extremely weak correlation, anti-correlation that Chuck commented about, but we're not very confident about how real it is without doing some more careful completeness corrections. And then let's look at what we really care about, right? How do we tie the escape fraction to other properties? So one thing I'd like to highlight is that all our sources are compact, like every known Lyman continuum leaker till date. And this takes on importance because the star formation surface density is getting very high in higher redshift. Another thing I'd like to highlight is that for the leakers that are not compact, you can play this sort of game where you can where you can look for where the Lyman continuum is leaking compared to the UV footprint. And then you can go follow up these regions with JWST NIRSPEC and see and ask what is special about that region versus like the surrounding region. And maybe it provides evidence for the channels and things that are being argued for. Another leaker that I'd like to highlight is this one, where I drew up this pixel-wise map of the UV continuum slopes. And the place where it peaks the most is the place where it has an O2 detection and is the place where Lyman continuum is detected. So maybe this motivates a new sort of tool where we create these beta maps and look for peaks and overdensities that imply some sort of channel. Finally, I want to show some X-shooter spectrum for this one source that was selected probabilistically in this earlier work in Naidu 2017, which goes slightly unnoticed because I used LYC candidates in the title. And this turns out to be an extreme O3, O2 source with double peak Lyman alpha with crazy lines that are seen in the local extreme star forming sample. And finally, just one comment on the state of O3, O2, which is this indicator that a lot of us have been looking at. So some of our sources actually lie in the MOSDEF survey, for which we have O3 and O2 measurements. And as you can see, they're kind of all over the place. which agrees with the isotope kind of figure, except it's at higher redshift, and this is the lower redshift picture. It's good that they match. And this is work that Daniel highlighted yesterday, which is basically taking an ultra-deep stack of O32 emitters and finding something similar. We don't really see a detection in Lyman continuum. Further, adding murkiness to the waters around O32. I'll leave the summary slide up. Apologize for the technical difficulties. Thank you for the extra couple minutes. And thank you all for being so wonderful at my first conference. Many of you are my personal heroes whose papers I read as an undergrad for the first time. So I actually read the whole thing. I knew that I didn't know that I had to skim and read only the abstract and see the figures at that point. So it's been a lot of fun hanging out with my heroes at my first conference, and thank you for being A+ people in general.
Okay, thank you. Okay, maybe just one question if you have.
A very quick one. At which redshift are the sources, the very faint one for which you have the Lyman continuum emission?
So all our detections, actually, that's something I didn't get a chance to emphasize. It's a really funny thing.
The following plot, so it's clear.
Sorry, go again?
Can you go to the following plot? Yes.
These.
The faintest one, yes.
So all our leakers are between redshift 3.06 and 3.36. So in our lower redshift sample, between 2.4 and 2.7, where you'd actually expect the IGM to be more gentle on us, be more kind to our cause, we actually don't find anything in that, any convincing leakers in the lower redshift window. So all our leakers are actually between redshift 3 and 3.4.
Okay,
thank you.
Thank you. Next speaker. Next speaker is Mohammad Safadeh. The impact of unresolved turbulence on the escape fraction of Lyman continuum photons.
Hi everyone. So I'm going to talk a little bit about turbulence and its impact on the escape fraction of Lyman continuum photons. We got a little bit of an introduction from Matt Leonard in the first day, so I'm going to just focus on this for a little bit longer. So this is how turbulence works. So you inject your energy at a scale length. It can be your supernovae or any other chaotic motion galaxy formation. So that sets the scale length for injecting the energy into the system. And that is called, well, that is on the left side. You can see at the largest scale, you input your energy, and then all you know is that that energy is going to dissipate. And you know that the dissipation is a molecular level process. So the dissipation happens at the smallest scale. So, you know, and then that depends on your viscosity, etc. And knowing these two facts, you want to connect these two scale lengths, and just right in the conservation of energy transfer, you get the, in between the inertial range, and you get a slope of like a -5/3, and these are like basic turbulent stuff. So the relation to astrophysics comes, I will talk a little bit like how this is directly related to astrophysical phenomena. But if you look at, for example, the simulations that are carried at supersonic isothermal simulations, you will see these beautiful pictures. This is the sliced cut from a simulation box that where you drive the turbulence by just shear modes. And then if you do the same with compressive modes, you get a larger dispersion in your box. As you can see, there are more holes or more porous medium when you drive it in a compressive fashion compared to a solenoidal fashion. And all I'm going to say today is that the vigorous turbulence can totally, of course, enhance the escape of the ionizing radiation. So if you look at the PDFs that you get from these simulations, you will notice that if you increase the Mach number of your flow, your PDFs become broader, and the peak of the PDF is going to shift to the lower densities. And this is the main reason why at a higher Mach number you will get actually a more probability for the escape of the ionizing radiation. And how you get this is that if I draw the same PDFs and if I integrate in a cumulative fashion, you will see that the top is the PDF, and then the bottom panel is the cumulative integration of the escape. And you will see that at high values of the overdensity, basically there is no contribution to escape of the ionizing radiation because it's just too opaque. But the good thing about turbulence is that you have moved a lot of material to, a lot of the volume is now filled with super low dense gas, which helps you to, helps for the escape of the radiation. And if you play this game a little bit further, you will see that if you choose your opacity, and then if you have different simulation with different Mach numbers, you will see that at higher opacity, the impact of actually resolving the turbulence becomes more and more important. And that is intuitively, the intuitive way to think about it is that, for example, if you have a tau of 10, basically nothing escapes. And if you have a little bit of turbulence, you can totally change that picture because you still provide a lot of sidelines through which the ionizing photons can escape. So this becomes more and more important at the boxes with higher and higher opacity. But if you just take one opacity and then just change the Mach number, this is what you get. Depending on the width and basically the width of the PDF that you assume for your supersonic turbulence, you will get basically around about a factor of 2-ish more enhanced chance of escaping the ionizing radiation. Now, this is just this is one effect, and then the other effect is that in supersonic turbulence, in turbulence in general, the neutral hydrogen fraction drops. So if you run a simulation with no background ionizing radiation, if you just run the simulation, you can see that, for example, towards the the first column, which is H, you will see that the red is without the turbulent impact, and then what you get from a cloudy simulation, and then the stars are what you get in the turbulent simulation. So you get a factor of basically 2 drop in H density just from the turbulent effect. So this is nothing to do with what I showed you earlier. So, but the combination of these two together helps you to get a factor of 3 and above. What you naively would expect to consider for the FSK. Are these high Mach numbers observed in nature? Yes, they are. This is the giant molecular cloud distribution in line width versus cloud radius. And yeah, and then there are these points. This is from Leroy et al. And then you can see these giant molecular clouds in NGC 253 that have been observed to have a high Mach number around 90. The typical Mach number for a molecular cloud is about 10, 11 in the Milky Way. But you can see that people start to observe like high Mach number in violent regions in local universe. So this is observed, and then we followed this up in sort of illustrative simulations. And what I'm showing here is the halo mass versus the mean Mach number of the star-forming gas in the galaxy. And you can see that I'm just showing you 3 different redshift slices. And What is evident is that at higher redshift, the average Mach number at the given halo mass increases. And now all you need to know about your simulation is that all you care about is basically the eddy turnover time scale, and you want to compare that to the star forming time scale of your simulation. So if eddy turnover time scale is short enough compared to your star formation time scale, then you cannot actually assume that the density of your cell is what you get from your simulation. You have to replace that density with what you cannot resolve, which is these log normal PDFs. So doing that will help you actually reconsider all the previous assumptions about the escape of ionizing radiation from galaxies in the simulation. So the whole motivation was that what happens to these simulations if we actually could resolve the turbulent cascade. So the answer is, well, if you can actually do that, you can get a factor of 3 or 4 higher ionizing radiation to escape from these galaxies at high redshift. So I'm going to end actually here and just repeat what I started with, and that is that the vigorous turbulence can totally enhance the escape of the ionizing radiation. Thank you.
Thank you very much. Questions? Matt?
So very interesting, Mohammed. I'm curious as to why you have that shift with redshift.
Yeah.
There, yeah, that one, in the turbulence. So what generates that?
So we believe this is due to filamentary feeding of the galaxies at higher redshift.
Right.
Yeah.
Right.
Yeah. But of course, I haven't done the. I just made this plot. Now I have to go back and look into confirming my hypothesis that this is due to the filamentary feeding.
I know it's still early, but do you have a sense of how that turnover time changes? Because I would suggest to you that, in fact, that time scale is constant across that diagram.
The whole time scale is constant?
Yeah, 10 to the 7 years is what you'll find.
For the eddy turnover time scale?
Yep.
Ah. Interesting. I'll look into this. Yeah.
Sorry?
I will look into this. I haven't measured
okay.
that. Yeah.
We can talk about it later.
Yeah, absolutely. Thank you.
Okay. More questions? Okay, well, thank you very much. Yeah. So, next speaker is Kimihiko Nakajima. He's going to talk on a hard ionizing spectrum in redshift 3 Lyman alpha emitters.
Thank you. Okay, thank you very much. So I'm Kimihiko Nakajima from NAOJ Japan, but actually I will be moving to another research institute in this winter to the Copenhagen Dawn Center. So yeah, but anyway, I'm from now Japan. So today I'm going to talk about the nature of the ionizing spectrum in Lyman alpha emitting galaxies at redshift 3. So based on the optical emission line diagnostics, we have realized that Lyman alpha emitters are interestingly characterized by an intense oxygen-3 emission with a high O3 O2 line ratio and large R2-3 index. And this result implies that Lyman alpha emitters are interestingly characterized by a highly ionized nebular region with a low gas phase metallicity. And as some of us have already discussed, we speculate that such a highly ionized nebular regions could be optically thin to the Lyman continuum emission, And the part of the ionizing photons might be escaping from these highly ionized nebula regions, or from the Lyman alpha emitters. And our recent deep HST imaging program named LACES indeed confirms that significantly high fractions of Lyman alpha emitters present prominent Lyman continuum leakage from our ratio 3 Lyman alpha emitters. And in addition, as reviewed by Daniel and Ryan, there are amounting evidence that support this trend that Lyman alpha emitters may present some significant Lyman continuum leakage. So we are now connecting these two important results to understand escapes of Lyman alpha and Lyman continuum escapes from galaxies. And for this purpose, the next important ingredient we think important is the nature of the powering source of these Lyman alpha emitters. So what kind of ionizing spectrum these galaxies typically possess. So to quantify this, we use measure of the Xi-ion parameters, defined as the number of ionizing photons per UV luminosity. So this quantity tells us an efficiency of the ionizing photon production from the stellar population. And based on the our pilot atmosphere observations, we have identified H beta emission from 7 Lyman alpha emitters at ratio 3. So by using this hydrogen recombination line, we can robustly estimate the Xi-ion parameter by directly counting the number of ionizing photons via the recombination physics. And this left histogram shows the distributions of Xi-ion parameters for our Lyman alpha emitters. So it is suggested that these Lyman alpha emitters typically possess a harder Xi-ion parameters than continuum selected galaxies. So this is very interesting and could be due to their young metal poor stellar populations. However, we still don't know if this is a typical characteristics of Lyman alpha emitters, because this left histogram is based on a small sample of our atmosphere pilot observations. So we'd like to confirm their properties using a larger sample or using different observational technique. And now we are interested in the less frame UV, ultraviolet spectroscopic data, because there exist several important high ionization lines, such as carbon-3, oxygen-3, and so on. So by combining these emission lines, we can address not only the gas phase condition in the interstellar medium, but also the shape of the ionizing spectrum from the stellar population. And especially, we are interested in the equivalent with very fundamental quantity, equivalent width of the UV lines, because they are directly linked to the Xi-ion parameter. So as I hope you can see in this example, equivalent width of UV lines should be, by definition, proportional to the number of high energy ionizing photons per UV luminosity. So should be described as a function of Xi-ion parameter. Oops. Xi-ion parameter. But of course, we are using the ionized metal lines. So this quantity should have some dependence on the metallicity and ionization parameter in the interstellar medium. So as for this dependence of the interstellar medium properties, we have recently constructed a large grid of photoionization models to interpret the less frame UV spectra, especially for high-Z galaxies. And this example shows our prediction of the equivalent width of carbon-3 as a function of metallicity and ionization parameter. But please note that this quantity depend on the stellar population, especially age. So, and here plotted models assumes the youngest stellar population age of 1 million years. So traces the maximum equivalent width for a given ISM condition. So if you assume an older stellar population, so you can predict evolution of the equivalent width of UV lines as shown in this light panel for the carbon-3 and carbon-4, I think, yeah. Of course, this evolution track depends on the stellar population models you assume, like star formation history, or single stellar populations, or binary stellar populations. So I will revisit this point later. But anyway, by combining these predictions, we now have the complete functional form of the equivalent width of UV line, so which allows us to examine the Xi-ion parameter using the UV line observations alone. So we need some data for our Lyman alpha emitters. So to obtain less frame UV spectrum for our ratio 3 Lyman alpha emitters, we carried out BLT BMOS spectroscopic observations. And so we primarily observe ratio 3.1 super narrowband selected Lyman alpha emitters. And this histogram, this shows distribution of the UV luminosity for our target Lyman alpha emitters. So our sample probes fainter galaxies than continuum selected galaxies that were previously studied. And with deep integration of BMOS, we successfully identified Lyman alpha emission from 70 Lyman alpha emitters. So this is some nice example. And this red histogram shows the number of identified Lyman alpha emitters as a function of UV luminosity and the equivalent base of Lyman alpha. So the success rate is very high even for the faintest Lyman alpha emitters, down to minus 90, or equivalent base larger than 100, 200, or could be 300. So it's very nice spectroscopic sample for Lyman alpha emitters. And among the 70 Lyman alpha emitters, there are about 10 Lyman alpha emitters that present tentative detection of the metal UV lines such as carbon-3, oxygen-3, and so on in the individual spectrum. However, these examples are very nice example, and generally in the brightest subset in a spectroscopic sample, because we are now most interested in the typical properties of Lyman alpha emitters, not biased toward brighter galaxies. So we have decided to make composite spectrum to get an average UV spectrum of representative sample of faint Lyman alpha emitters. And to see some dependence among the Lyman alpha emitter population, we split the sample into two subsamples based on the UV luminosity or equivalent base of Lyman alpha and make composite spectrum. And these generated spectrum nicely demonstrates that we have successfully identified the faint UV emission like such as carbon-3, oxygen-3, and maybe carbon-4, so at a moderate significance level in the stacks. So we are very happy with this stacking analysis. And we have also quickly checked that our stacking analysis confirms the positive correlation between the equivalent width of Lyman alpha and carbon-3 as previously suggested. So please also refer to the Francesca's talk by using the boundless, more nice data. And anyway, and hereafter we call these blue symbols as the stronger Lyman alpha emitters, and orange as the weaker Lyman alpha emitters because they behave very similarly in the following analysis. Okay. So before ion, we first need to determine the gas phase properties like metallicity and ionization parameter. And for this purpose, we make use of this UV diagnostic diagram using carbon-3 and helium-2 lines. And on this plot, we realize that these stronger Lyman alpha emitters, blue symbols, stronger Lyman alpha emitters tend to have smaller value in this x-axis than the weaker Lyman alpha emitters. And we think this difference originates from the metallicity difference between the two subsamples. So this right panel presents again our photoionization model tracks. So this x-axis value becomes larger with a higher gas phase metallicity. So by using models to our data points, so we obtain that these stronger Lyman alpha emitters are typically characterized by low metallicity, about 20% of the solar metallicity value. And the weaker Lyman alpha emitters have a factor of 2 higher gas phase metallicity. And we also constrain the ionization parameter with metallicity. So by using these determined gas properties, we can now address the Xi-ion parameter by using the observed equivalent width of carbon-3 lines, the strongest UV lines. And they're plotted here and here for UV line analysis. And so we are using these model predictions to interpolate the Xi-ion parameter. But as we fit our data point, we notice that stellar photoionization models, including massive binary systems, are really necessary to reproduce the strong carbon-3 emission, especially for these stronger Lyman alpha emitter populations. So by using these massive binary star models, we obtain that this stronger Lyman alpha emitter, this blue one, really needs a very hard Xi-ion parameters typically. And for the weaker ones, slightly lower, but still, hard Xi-ion parameter is, derived for the weaker ones as well. So if we overplot these, results on this histogram that I presented with the H-beta observations, so they are plotted here, so the range here and here. So these UV line analysis, remarkably reproduces the hard Xi-ion parameters as suggested for the Lyman alpha emitters with H-beta observations. So, it is highly likely that this kind of hard ionizing spectrum is a key properties characterizing galaxies with a strong Lyman alpha emission. And importantly, their hard Xi-ion parameter is not due to their faint UV luminosity. Here plotted as Lyman break galaxies or continuum selected galaxies Xi-ion parameter as a function of UV luminosity. So they almost present uniform Xi-ion parameter over the 3 magnitude. And if we overplot Lyman alpha emitters on this plot, these are the individual Lyman alpha emitters with H-beta observation and our UV stacking analysis in this talk. So these Lyman alpha emitters present a consistently higher Xi-ion parameters than continuum selected galaxies, even for given UV luminosity. So it is very interesting, and probably this is a unique characteristics of Lyman alpha emitters. So the takeaway message from this talk today is the possible impact of this hard Xi-ion parameters for Lyman alpha emitters on the other interesting Lyman alpha emitter properties like high oscillator ratios, or could be high fractions of sources with Lyman continuum detections. So as a summary, to explain these unique properties of Lyman alpha emitters, we speculate the efficient production of ionizing photons, play, a key role. The powering source of Lyman alpha emitters would produce, a large amount of ionizing photons efficiently into the interstellar medium to achieve highly ionized nebula regions. And this could be due to the, a young or bursty, star formation event in the low mass young galaxies of Lyman alpha emitters, or massive binary stellar systems could play a role in shaping the blue ionizing spectrum in Lyman alpha emitters. But in any case, the achieved highly ionized nebula regions could be optically seen to the Lyman continuum emissions, so which result in a higher chance for ionizing photons to escape from Lyman alpha emitters than from continuum selected Lyman break galaxies. Okay, so this is one illustration of Lyman alpha emitters that we obtained based on our spectroscopic observations so far. Okay, yeah, that's it. Thank you very much.
Thank you very much. Questions?
Hey, nice talk and really beautiful data. One question, that's something that was on the side of your slide that I wasn't sure if you said. When you were using the BPAS models, were you using a 1 megayear age, population age? Were you using a 1 megayear population age for the BPAS model? Is that what it said on your slide?
For the line ratios.
Yeah.
Yeah, it is. Yeah.
Interesting. So,
yeah.
So how do you interpret that? Were you just doing that? Do you think that seems unrealistically short to me for the average of many galaxies that you could have caught every single one of them at the just in the first million years of star formation? Do you have a different interpretation of that, or do you just feel that you had to go that the models, maybe there's another way that you could have an even stronger ionizing production, harder spectrum that BPAS models currently provide?
I see. Yeah. It is once. Yeah, I have to again mention that this for the line ratios, because we thought this line ratio is most sensitive to the most massive stellar systems, and which is sensitive to the youngest stellar system. So we for this line ratio diagrams, we assume the youngest 1 million years stellar population using BPAS or other single stellar population models, and it is true. This line ratio should also have some dependence on the for example, a few million years. The massive Wolf-Rayet stars or could play a role in producing some helium-2 ionizing photons and could change the line ratio. So it is true. We have some more space to explore these line ratios by varying the stellar age of the stellar population. Yeah. Thank you.
One more question.
Hi, Kimiko.
Hi.
Thanks for this wonderful talk. I just wanted to point out that in the talk that I gave today morning, a lot of the non-detections that we saw were from the beautiful Muse-wide and Muse-deep survey areas. So all of them were also Lyman alpha emitters. So in our linking of Lyman alpha emitters to Lyman continuum escape and an increased rate, at least our sample doesn't seem to bear that out. So I was curious if you like had.
It's a good point. I think it's of course still under debate, and if there's a really trends that Lyman alpha emitters tend to have a higher escape fractions or higher chance of finding a counterpart in the Lyman continuum image, and so in your sample you also have the Lyman alpha emission spectroscopically, and there's no clear trend between the Lyman alpha emitters and more non-Lyman alpha emitters in terms of the Lyman continuum escape.
Right, so we've looked at like maybe 300 plus.
This is something very interesting, and I agree. This, we have to need more larger sample to conclude that there's a really close connection between the Lyman alpha and Lyman continuum escapes for the galaxies. Let's talk more later. Thank you very much.
Hello, my name is Céline Perroux and I'm based in Marseille. Currently I'm seconded in Ido in Garching. And indeed I'm going to say a few words about the physical properties of the circumgalactic medium. I'd like to start with this picture which shows how we think this is taking place. So we believe that accretion of metal pore gas through cosmic web filaments feeds galaxies, and this gas cools down through Lyman alpha radiation to form the molecular dense gas that is the fuel for star formation. Then supernovae and AGNs will launch galactic winds that will in turn pollute the surrounding of galaxies with metals and energy. And most of those processes, we believe, are taking place in this so-called circumgalactic medium, which is a loosely defined term that is looking at 300 kiloparsec scale gas around galaxies. In the last few years, we've been using unrelated bright background sources, such as quasar, to study this gas for two reasons. First, it allows us to reach low-density gas, and second, the technique is insensitive, it's independent of redshift. So our sensitivity is similar at high redshift or at low redshift. It depends on the brightness of a background source. So I'm going to say a few words about what we know about the physical properties from observation of the CGMs. Because of time limitation, I'm going to cherry pick some examples. And I would start with this picture, which is showing how we try to relate the stars and galaxies that we see in emission with the gas around galaxies that we probe in absorption. And to do this, we've been using 3D spectroscopy, which is an image where every pixel is a spectrum that provide a lot of information about the kinematics and morphology of those objects. And in that field, Muse, of course, has been a true game changer, providing wide field optical IFUs for a number of fields. So here I'm showing on the left one quasar field. So the quasar is the center. The left panel shows the HST image. The right panel is the Muse white light image. And this field is known to have an absorber at a redshift 0.3 with a H1 column density of 21 and absorption neutral gas metallicity 16 solar. And we've taken this cube and performed a so-called narrowband cut at the expected position of the emission lines given the redshift of the quasar, and we find that there are 11 galaxies at the absorber redshift. 7 of which are new discoveries. So this is a low redshift exercise. We are reaching star formation rate limit of 0.01 solar masses per year. And among those galaxies, a number of them are quiescent objects that are not detected in emission, but are found in continuum, and the redshift is determined thanks to the Balmer break. In particular, I'd like to point out G0, which is the closest galaxy that we found close to the quasar at an impact parameter of 10 kiloparsec. So you see that there is some evidence for structure in the way those different galaxies at that redshift are aligned, possibly tracing, filamentary structure or a small a small group of the order of halo mass of the order of 10 to the 12 solar masses. So we've been observing this same field with ALMA to probe the molecular gas. 3 of those objects are detected in CO1 to 0, as are shown here. And we find very large H2 masses of the order of 10 to the 10 solar masses. So those objects have low star formation rates, so that leads to a very long depletion time from 2 to 12 gigayears. So we are looking at objects that are very inefficient in converting their gas into stars. So I'm going to show more of this data. For those that are less familiar with those kind of data, the left panel is squared, and that's the Muse data. The right panel is round, and that's the ALMA. This is now, I've removed the quasar from the center of the field. This is shown as a white square in the plane of the sky, and I'm again rotating narrowband fields around those emission lines. The cone-like structure you're seeing are objects that are detected in continuum as a function of wavelength. The knots are the ones that are detected in emission only. And luckily, band 3 ALMA primary beam nicely matches Muse 1 archimedes field of view, and in the contrary, Muse breaks the one-line detection degeneracy of ALMA. So combining those two observational data sets is very powerful. So you see also that there is evidence for structure and velocity fields in those objects. We can study in details the kinematics of both the ionized gas and the molecular gas in those objects. So I'm looking at one of the most brightest, more massive objects near the quasar, just to show an example of what we are observing. And the top line here, the left panel shows the HST continuum image. The middle panel shows the narrowband, again, H-alpha Muse image. And on the right, I'm showing a modeled velocity field from forward modeling using an MCMC chain that fits in 3D space 10 kinematical and morphological parameters. So even in poor signal-to-noise data sets, we are able to recover the kinematics of those objects. The bottom line is showing the ALMA CO detection, the spectrum, and the image, and again, the modeled velocity field. So we see that those velocity fields, both in molecular gas and ionized gas, are nicely matching each other in terms of orientation. The Vmax are different, so we are looking at more concentrated CO gas than we see in the H-alpha. Those Vmax leads to estimates of dynamical masses and halo masses for these objects, and we, as I say, have also an estimate of the molecular mass. So the question, of course, is what is this gas? And I like very much this picture. I'm showing here the magnesium-2 absorption spectrum of a background quasar set at a velocity position of 0, where G0 galaxy, the one with the smallest impact parameter, lies. And I'm showing the position of the different galaxies going from bottom to top as a distance from the quasar line of sight. So this is the angular separation. The green bars here are showing the Vmax for each of those galaxies for which we've been able to recover the kinematics. So what we're finding is that the absorption we see is not well explained by the galaxies that are closest to the quasar line of sight, and it's not consistent with the kinematics. So to further understand what we're looking at, we've referred to some cosmological simulation. I'm showing here the same field in H alpha, and to the right here is a zoom-in simulation using a Mach mu spectrum, if you want, so it's the same field of view. It's the same flux colored bar scale here, and I've picked a halo with star formation rate and halo mass that is matching our observation. And what we're seeing is not one, but several objects, pretty much like we are observing, and the fluxes are very comparable to what we're observing. Now, in the simulation, if we play the exercise and go deeper, 4 orders of magnitude deeper than we can currently do with osmosis data, we find all sorts of gas that is, remnant of merging and tidal stream that would be very difficult to probe with current observations. So I think absorption is still a way to reach this very low density, low surface brightness gas. And in fact, if we go back to the white light image of MUSE, some of the massive galaxies show some indication of this gas trail. I'd like to present some new work that is looked at, especially the metallicity distribution in the CGM. There have been the idea that the metal that is ejected through galactic winds is probably mixed with the IGM, perhaps in kiloparsec scales, but we've heard also of other scenarios where we would have Pascal scale cloudlets that will explain the cold gas that is being observed. So far, people have often used multiple lens quasar background images to look at how the absorption metallicity may vary on fairly large scale, and that gives us information about the so-called current length. In our new work, we've looked at not multiple images, but extended bright background galaxy. And that's very powerful because potentially there are a number of such targets, but also our findings are independent of lensing modeling. So we've been very lucky to find in one of our MUSE cube 2 very bright galaxies at redshift 1.15 that happen to have a magnitude 2 absorber at redshift 1. And this magnitude absorber is matched by 2 O2 emitters. One of them is only 21 kiloparsec away from the quasar line of sight. Most importantly, those bright galaxies form an area of 30 kiloparsec square at the redshift of the observer. So we've been able to construct this equivalent with maps that is looking at the spatial variation of the metal absorbers over this area. So I've divided galaxy A, which is the brightest, into 4 regions, fairly ad hoc, but that leads to a signal-to noise in the continuum that is matched in each of the region. And we find that the equivalent width of the magnesium-2 doesn't vary much on those areas on scales of the order of 8 kiloparsec. The faintest galaxy, BGB, we don't see the equivalent with the magnesium-2 against that spectrum, although we have a sensitivity to see it. And that's on scales of 25 kiloparsec. So using assumption that we are looking at spherical cloud of metal gas and giving the non-detection on scales of 25 kiloparsec, we've been able to, including the density, our knowledge of the column density of the gas, measure a mass of metal clouds of the order of 10 to the 9 solar masses. So I think this work is potentially can expand because those galaxies, I believe, could be observed with a further facility, maybe GWST and Harmony on ELT. And again, this is work that is not relying on lensing modeling. Now I would like to say a few words about the emission that may come from the CGM. So, of course, the absorption techniques indeed, is limited in terms of spatial information. So to revert to emission would allow to map the CGM and perhaps also to concentrate more on Lyman alpha and look for gas that is perhaps metal poor. It's difficult. We expect the signal from emission of the CGM to be very faint, and maybe dedicated instrumentation will be required. So we've heard yesterday about this beautiful result from the MUSE GTO team showing those halo that are now detected not in stacks but in individual objects down to surface brightnesses of 10 to the minus 19 or lower, and at redshift 3. What we've been looking at in our team is whether we could look at the CGM at lower redshift. And for this, we have designed and built a balloon-borne UV spectrograph, a multi-object spectrograph with a 1 meter mirror. This is observing at 200 nanometers, that's Lyman alpha at redshift 0.7. Fireball is a collaboration between Caltech, Columbia, and Marseille. The PI is Chris Martin, and a large fraction of the team is currently on the launch site. We're hoping to launch anytime soon. So what we've been doing is, again, revert to Ramses cosmological simulation to try and understand what we should expect for such an experiment. We've been using Ramses AMR code, and we've seen some of the beautiful work that has been done in terms of predicting Lyman alpha emission at high redshift with such codes. The specificity of our work is that the simulation is evolved to redshift 0 with the idea to provide something that is suitable for something like Fireball. The box is 14 megaparsec. We are reaching a spatial resolution of 380 parsec. So there's no thermal supernova feedback and on-the-fly self-shielding. We have post-process simulation to predict the expected emission from the CGM. We have included photoionization from the UV background and collisional ionization. And for the Lyman alpha, we include some scattering from the ISM. So here is one of our halo. I'd like to emphasize this work has been led by Ramona Augustin, one of my PhD students, starting now her third year and looking for a postdoc. She's done beautiful work doing this simulation for Lyman alpha that I'm showing here, but also some other metal lines. We've looked at carbon 4 and oxygen 6 to try and understand what we could expect with such an experiment. As an aside that I think is maybe of interest to you, of course, this prediction of the Lyman alpha flux from the CGM are heavily dependent on the escape fractions that we assume. I'm showing here the Lyman alpha flux as a function of redshift. The data points are measurements from Galax, from Dervin and Wold, and the stars show our predictions. The pink is for an escape fraction of 1%, and the brown stars are for an escape fraction of 0.1%. And of course, we have a very simplistic treatment of this currently. So what we do with this simulation is we've developed a full model instrument, and we feed that model instrument with simulated cubes that provide us an output observable that we now data reduce. We subtract the continuum from the galaxy to retrieve the CGM signal, and we build this signal-to-noise cube that you see here on the right for a number of the cubes that we have simulated. And what we are finding is that the Lyman alpha we expect at those redshift will be nicely detected with Fireball. It's possible that some of the objects will be faint. So I'm not showing the predicted signal-to-noise as a function of magnitude. The data points are those halos that we've simulated for different lines. So Lyman alpha is shown in orange, carbon 4 is shown in blue, and oxygen 6 is shown in green. Since Fireball is a multi-object spectrograph, we are hoping to be able to stack many of these objects and reach even deeper magnitudes to detect this CGM in some of those galaxies. And that's shown here with dash and solid lines for two optimistic and pessimistic assumptions. And so you see that if you could stack 100 spectra, you can reach very deep observation. We've also used the similar simulation to look at the high redshift, and we had in mind one of the first light instruments for the European ELT, Harmony. Harmony is again an IFU working from visual to infrared. It's a small field of view. But we've looked at what is the signal-to-noise that we expect for such data, and we compared with current facilities like Symphony, but also Muse. So remember, the harmony field of view, the largest field of view for harmony is only 6 by 9 arcseconds, so it's significantly smaller than Muse. But notwithstanding the non-optimal mirror coating for the ELT, this kind of photon-starving science may benefit from the large collecting area of the mirror of ELT. And we find that harmony may be 20 to 30% more sensitive than Muse in the CGM regime. And in particular, there are fluxes that will be difficult to detect even with the deepest Muse observations that would be visible and reachable for harmony. So with this, I would like to review some take-home messages. I've illustrated what we've learned from CGM properties, from looking at the kinematics. I haven't talked about the metallicity of the CGM that we have been observing with quasar observers. One thing that puzzled me, and I would really much like to see some simulation perhaps helping us to understand how come we are finding this very cold molecular gas in H1 selected quasar observers. That's unexpected to me. So we are finding that they probably are inefficient in converting their gas into stars. I've presented some new work looking at the spatial distribution of metals in absorption against extended background sources. I think this has a potential of telling us about kiloparsec and maybe eventually parsec scale gas clouds. And I've shown some prospect of looking at the brighter CGM emission at lower redshift using new UV facilities. Thank you.
Thank you very much. Questions? Gerhard?
You derive metallicities, for instance, for the CGM. You take ionization equilibrium into account. But do you have another recipe or so to derive the temperature, whether the ionization equilibrium is really available?
So you're asking about the temperature in the simulation?
No, not from the observations.
Ah, sorry.
You have different ionization stages. You could, for instance, determine the temperature according to the ionization levels or ratios, but taking the ionization equilibrium into account. But do you have another recipe, for instance, to determine whether the temperature is correct? I do not know. I'm not an observer, sorry.
Yeah, so you're asking about the temperature of a gas that we are probing with quasar observers that are almost always showing maximum 2 absorption lines like I'm showing. So this is believed, to be cold gas, 10 to the 4 or so gas. There are thoughts that, carbon 4 will trace slightly higher temperature, and oxygen 6 will be more tracing 10 to the 6 Kelvin. To come back to your questions, what we do observationally to understand what's the ionization potential is indeed we use elements with different ionization excitation and run photoionization model and making, I think, a lot of assumption about the geometry of the gas and the incident UV flux. But from this, we can get some constraint on the typical ionization potential in those observers. Yeah.
More questions? Okay, well, thank you, Celine, and thank you to all speakers. We have a break till 11 o'clock.